Hi, we're starting a new project in which I'll try, in my broken English, briefly explain something about the most interesting papers which appeared in the astronomical part of the archive. So let me start with an explanation about the archive itself. Here we are. This is the website of the archive. And here we see that there are many different subjects covered by the archive, and altogether there are more than 2 million articles there. The project was formed about 30 years ago, and the authors put their scientific papers in the original form or sometimes in the final form to the archive. This is an absolutely legal process, by the way. And so all these articles are in open access, which is a great advantage. Here is the astrophysical part, and we can have a look how many papers are published now. Let me take the last year. And we see that each month, just in the astrophysical part of the archive, more than 1,000 papers have appeared. Again, I repeat, every month. And also there are about 200 papers which are cross-listed to the astrophysical part of the archive from other parts of the archive. For example, from gravity and cosmology studies, from nuclear physics, and so on. So every morning I start my day with reading the archive, and slightly more than 20 years ago I started a project in Russian in which I briefly explain which papers appeared the most interesting for me. And now we'll try to do nearly the same, but in English, and not in the form of a website, but in the form of video lectures. Okay, let me start. I'll tell you about a dozen of papers on different subjects. And the idea is not to select actually top 10 or top dozen, the most interesting papers of January in this case, but to show you the most interesting papers, in addition to show you interesting papers, which maybe are not so important, but still they are quite interesting, and they cover interesting subjects, or they are related to some interesting studies, and so on. But let me start really maybe with a top result published in the astrophysical part of the archive in January. Here is the paper. The authors used archives of gamma ray burst observations. They used archives of different observations from different satellites. As you know, gamma rays are absorbed by the Earth magnetosphere, by the Earth atmosphere, and so it's necessary to put detectors above the atmosphere, which means you have to put them on a satellite. And what was the idea? Actually, people tried to do a similar thing many times before. People are looking for quasi-periodic oscillations in gamma ray bursts. Now we know that there are two types of gamma ray bursts. They can be long, and in this case we're dealing with the collapse of a massive star, most probably with a black hole formation, but not necessarily. In many cases, probably magnetars are formed, neutron stars with large magnetic fields. But also there are short gamma ray bursts. And in this case, we are sure that we are dealing with coalescence of neutron stars. In one case, as you know, there was a simultaneous detection of gamma ray signal and a gravitational wave signal, which happened in August 2017. So the hypothesis that short gamma ray bursts are due to coalescence is really confirmed, directly confirmed. So people were looking for some periodicity inside the sources, and never before the researchers really succeeded. So here we have two first and solid examples of such quasi-periodic oscillations. In the picture, you see these two bursts. Here are their numbers or names. GRB means gamma ray burst, and then the date. So this guy was detected in 91, this in 93. So this is not a new data. But the authors of that study used some new approach to look for these quasi-periodic oscillations. And in the time intervals denoted by these vertical lines, so for the first lot, for the first burst, in the first plot, and for the second one, they detected quasi-periodic oscillations of very high frequency, about 2 kilohertz. And this is a very interesting result, because most probably we really see oscillations of a neutron star. Let me find another picture to show it to you. Here we are. So again, time is in the horizontal axis. Please note that bursts are really short. Time is in milliseconds here. And in the bottom plots in each of the two panels, we see frequency. And here, denoted by these arrows, and here, again, denoted by arrows, you see these oscillations. So the typical frequency is about 2 kilohertz. That's a lot. And this might represent oscillations of neutron star. And this is really very interesting, because this is a new probe of physics of neutron stars. Neutron stars most probably are the most interesting physical objects, physical bodies in inanimate nature, and it's quite interesting to get a new tool to study them. Okay, let's move on. The next paper. Now about black holes. Some people think that black holes are more interesting. Who knows? Black holes are mysterious. Neutron stars are really interesting because you see all the physics. For black holes, often you don't see lots of physics. You just can imagine it. You can make theories. But still, there are very interesting processes which for sure exist in nature. And one of them is called the gravitational wave rocket. It was shown quite long ago, a few decades ago, that when we have a coalescence of two black holes, then the black hole which is formed as a result of this coalescence gets velocity. It is kicked. This happens because gravitational waves are not symmetrically emitted during the coalescence. Of course, you can by hands make an absolutely symmetric process, but this never happens in nature. So gravitational waves are emitted non-symmetrically, and gravitational waves carry momentum. So to conserve the momentum, it's necessary that the remaining black hole also gets some velocity. It's get kicked. And it was shown that typical velocities in this case are about few hundred kilometers per second, which is a lot. 500, 600, 700 kilometers per second, it's enough to leave the galaxy, for example, to escape from the gravitational wave potential, from the gravitational potential of the galaxy. In some cases, during coalescence, you can get even higher velocities. But what is typically assumed? Typically, it is assumed that black holes follow circular orbits, well, nearly circular. It's a coalescence, so it's a kind of a spiral, but the eccentricity is very low. And this is a quite reasonable assumption, because in most of astrophysical situations that might be the case. But still, gravitational wave observations demonstrate that sometimes eccentricity might not be zero. And in this paper, the authors studied, say, an opposite case, not circular orbits, but collision of two black holes. And it was suspected that in this case, the kick velocity, the recoil velocity, can be much larger. And they explicitly showed it with direct calculations, which take into account many different parameters, assumptions. So these plots are made for black holes of equal mass. And what is changing is the spin characteristic. So black holes rotate, and so we can have different frequency or velocity of rotation, and we can have different orientation of spin axis of the two black holes. And it's quite interesting to see what can be the maximum recoil velocity in the case of black hole collision. And in this plot on the left, on the bottom plot, you can see, so on the vertical axis we have the peak velocity. On the horizontal axis we have the impact parameter, and we see that in some cases the velocity can be nearly 25,000 kilometers per second. That's really a lot, guys. That's really a lot. It's nearly 10% of the velocity of light. And this is quite impressive for me, I'd say. Of course, such processes which result in black holes moving with such huge velocity might be rare, but they are quite possible. So, in my opinion, this is a very interesting result. Okay, now from gamma ray bursts, coalescence, we come to fast radio bursts. Fast radio bursts have been discovered in 2007, so this is a new phenomenon in astrophysics. It's not completely understood yet. There are many interesting puzzles, and what is important also is that fast radio bursts can be an important tool. They can be probes of interstellar medium, intergalactic medium, circumgalactic medium. And so it's very important to find more and more of fast radio bursts. And 10 years ago, it was shown that some of sources of fast radio bursts can produce repeating events. So most often, now there are more than 1,000 fast radio bursts registered. Mostly often we do not see repetitions. But there are few dozens of sources which produce repeating bursts. And the sample is growing, and this is really important. Now the main instrument is the Canadian radio telescope CHIME. And in January, they released their new catalog of repeating sources. And the number is doubled. You see it on the map. The instrument is in Canada, so of course they observe mostly northern sources. So it's not a miracle that there is nothing on the south, simply they don't see that part of the sky. So that's easy. And we see that now we know 50 repeating sources, and 90% of them are discovered by CHIME. And the new catalog really doubled the sample, so they presented 25 new repeating sources, which is really very important. So the sample is growing, and of course, we're not just interested in increasing the sample. We're interested in understanding the physics. And sometimes it comes not with large samples, but with interesting discoveries of even a single event. And in January appeared a paper about a very interesting fast radio burst, which allowed to estimate an important parameter of our galaxy. So here we have a clear, nice example where a fast radio burst is working as a probe. It's a probe of circumgalactic medium. The burst is not very usual in the sense that it's situated not far from our galaxy, and the host galaxy of this burst is well identified. You see it in the picture. The burst by itself is quite regular. We can have a look at the light curve. Here it is. Yep. Polarization is measured for this burst. The burst is quite bright, so you see signal to noise ratio is about 30, which means it's quite bright. Frequency at which they observed is in typical frequency, 1.4 gigahertz. Duration of the burst is not that typical, it's really short. Again, please note that the time is in milliseconds here. But what is important really that this burst allowed to measure properties of the circumgalactic medium of the Milky Way. It's not very easy to do it in general, and so any new measurement can be important. And in this case, it is important. As the circumgalactic medium is more or less symmetric, it's not, of course, absolutely spherically symmetric around the galaxy, but still, even one precise measurement can allow to have an estimate of the total mass of the circumgalactic medium. And in this paper, the authors obtained such an estimate, and it came out that the circumgalactic medium of our galaxy is slightly less massive than it was expected. Slightly means a factor of 2, which I would say is not a lot for such things, but it's a quite interesting result because now people are really starting to probe circumgalactic medium of many different galaxies with different methods. And even the subject is so developed now that also recently, occasionally, appeared a nice big review. So you see 69 pages, a nice review about physical processes in circumgalactic medium. So those who are really interested in the subject are welcome to look at this review. It's very informative and quite understandable even for non-professionals exactly in this narrow field. Okay, very often astronomers are asked what's the usage of astronomy? Isn't it just a waste of money to study such fundamental science as astronomy? Of course it is interesting, but it's like maybe like sports, different kind. Still there are answers, and real astronomical discoveries help to develop new technologies. And in last few decades, a very interesting field appeared. It came out that the best available way for navigation in the solar system is based on X-ray observations of radio pulsars. So radio pulsars, like the Crab pulsar, for example, they emit the whole spectrum. You can detect their radio pulses, gamma pulses, and everything in between. And for many radio pulsars, we have X-ray detection. That's one point. The second point is that radio pulsars are very stable sources, and each has an individual mark, the spin period. So you can easily distinguish at which pulsar you are looking at because you measure the spin period. And development of X-ray astronomy resulted in a simple fact. X-ray observations of bright sources are really very cheap now. You can have a very light detector which doesn't require large power, and it can very well measure positions and spin periods of pulsars observed in X-rays. And this is the best way for a navigation system which doesn't require continuous contact with the Earth. With several tens of pulsars on the whole sky, you can easily determine the position of the satellite somewhere in the solar system far away from the Earth. And also, which is very important, you can measure the velocity of the satellite. Because if you are moving towards some radio pulsar, then the period that you measure is slightly shorter due to the Doppler effect than it might be. If you are moving away from a pulsar, the effect is opposite. You have a redshift. Okay, so I would say all major space agencies are developing instruments based on this idea. So the Chinese Space Agency already had 2 tests on satellites. NASA had tests on the International Space Station with a nicer X-ray telescope. And in this paper, the European version is presented. Well, maybe not exactly this installation, not this device will be used for real satellites, but in my opinion, it's an interesting and important step. And really, in few decades, interplanetary stations will use a different kind of navigation system from what is used now. So astronomy is useful, believe me. Okay. Also, there is another example that astronomical studies can be very useful, in a sense profitable. If you think about scientific problems of great value for the humankind now, and even great value can be measured in dollars, euros, or whatever you like, then the answer might be that the problem is the problem of the Earth climate. We want to understand the Earth climate, how it changes on a short time scale, on a long time scale, on intermediate time scales, but we don't have very good models for that. We do not understand completely physics of the climate. And our experience shows that if we need to have a precise model, then to understand the physics better, we have to probe the model with very different real objects. Really different objects with very different properties. And exoplanetary studies give the possibility to probe climate models in very different conditions. And this might result in better understanding of physics, in developing of new software, and also, which is very important, in growing of a new generation of scientists who can work, who have experience and education to work with complicated climate models. And in this short review, the authors present their studies, so it's not a very broad review, of climate models for Earth-like planets. This is very important because now we are really starting to probe atmospheres of other planets. For planets like hot Jupiters, this is a usual thing even now. For Earth-like planets, it's not the case. But still things are moving on. James Webb is in orbit, and James Webb is one of instruments which can tell us much more about atmospheres of planets, including potentially habitable planets. In a few years, the European Space Agency will launch the satellite Ariel, which would study atmospheres of exoplanets. 40-meter ground-based telescope will start operating in a few years, and this instrument also will add a lot to our knowledge of exoplanetary atmospheres. So really the field is developing, and in my opinion it's very useful for the whole humankind, because we will have much better models for the Earth climate. And this paper, just for those who became interested in the subject, is just a tiny example of what people try to do. In the plot on the left, for example, they calculate the habitability for Earth-like planets around solar-like stars, and on the vertical axis is the semi-major axis, on the horizontal axis the eccentricity, and these yellow islands are regions of high probability of habitability, for the habitability that the planet is potentially habitable. And this corresponds more or less to the Earth, yes, one astronomical unit, nearly zero eccentricity, but it's interesting that there is another island. And the authors used particular climate model, and it was developed together with scientists who study the Earth climate. So it's quite interesting example. Of course, we can study in details atmospheres of planets in the solar system. Probably Mars is the easiest subject for such studies, and the next is Venus. And you know that there are many discussions now about the existence of phosphine in the atmosphere of Venus, if it has biological origin or not. And in January appeared the nice review. I really liked it, so I recommend to look through it, about all these subjects. In the picture you can see an artist's conception of early Venus. It is quite possible that a few billions years before, the climate on Venus was quite different and it was much softer. Now, of course, Venus is a very unpleasant world for us. But before it was not so, and in this review, the author covers really all subjects related to these problems, and if you need more details, you can just follow the links. Okay, now we come really to exoplanets. And in January, there was one nice original study. Well, actually, there were many nice original studies, but I'm going to talk about just one of them. The authors of this paper did a quite useful thing, useful for the whole community working on exoplanets and related subjects. They took all data obtained by Kepler in K2 phase of observations and tests, and they determined the parameters of the host stars of exoplanets in a uniform way. This is very important because what typically happens? Different authors study different exoplanets and different stars. So they use quite different approaches to determine the stellar parameters. Then it's all collected in the database. And also in January appeared another review about host stars of exoplanets. Here it is. And we see the Hertzsprung-Russell diagram for these stars. And here they just use, the author used this archive, one of the best archive of exoplanets, and just grab data on the luminosity and effective temperature of stars. But it is important that these data was determined in a non-uniform way. So different authors used quite different approach to determine luminosity and effective temperature of stars, not saying about other parameters like the radius of the star, which is not directly measured. It is calculated on the base of some stellar models. And different authors can use different stellar models, or even the same model, but maybe with a different set of parameters. And here, the authors use a unified approach. And this is very important, because in this case, you really can compare these thousands of stars with each other. You can plot them in one diagram, being sure that systematic effects are the same for all stars. Of course, there can be some errors, some differences with reality, but still systematically they are the same, and this is a very important study. So no doubt that this result, this paper will be very useful for the community in the future. Okay, let us change the subject completely and think about new astronomical projects. And new astronomical instruments, they are built in Earth, in space, and very often people ask, why don't you build an observatory on the moon? And the answer is simple, we don't need it. It's much cheaper and better with the present technology to put telescopes in orbit, on low orbit around the Earth, on the International Space Station, or maybe put them in the vicinity of L2 point, and so on. It would be very complicated to build something on the moon, because you have to take very expensive and very delicate, very fragile device, and not just put it into the space, but also to land on the moon, and then somehow to assemble everything together. It's complicated and expensive. But there is a unique task which really requires observations from the moon. And these are low-frequency radio observations. In this respect, the other side of the moon, which is not always dark, but listening to Pink Floyd, of course, you are always tempted to stay on the dark side of the moon, on the opposite side of the moon. Position on the opposite side of the moon is unique because you do not see radio noise from the Earth magnetosphere. And this is very important for low frequencies. We can observe from Earth down to a frequency of roughly 100 megahertz. And LOFAR in the Netherlands is a wonderful instrument which produces lots of interesting and important results. But we also want to go to lower frequencies. Why? There are many reasons. Of course, simply we want to observe in the whole spectrum. Maybe there is something interesting there. That's one task. But in some cases, we really know that there is something interesting because there is a cosmological redshift. Most probably you heard about the wavelength 21 centimeter. This is the wavelength at which the neutral hydrogen is emitting. And it's very important for astronomical studies. But if you are looking at faraway galaxies, so you look further and further into the past of the universe, then you receive a redshifted signal. And so the frequency goes down. It is 1.4 gigahertz for a nearby source. But if you go to redshift 100, roughly, then the signal is 14 megahertz. And if you want to observe a neutral hydrogen in these dark ages, you need to go to low frequencies. And the only way is to put the radio telescope, maybe not the only, the best way is to put a radio telescope on the backside of the moon. Luckily, radio telescopes working in this range can be very simple. And different space agencies are developing several different projects to fulfill this task. And the leaders are the Chinese agency and NASA. The European Space Agency is also taking part in this development. And in this short note, you see just 4 pages. The authors present one of American projects, Lucy, which is supposed to be a low-frequency radio telescope on the backside of the moon. And it's really quite interesting. So no doubt in a few years we'll have a prototype. Well, the Chinese prototype was already there, but there were some problems with it. In a few years we'll have a better prototype, and in 10-20 years maybe we can expect a full-scale instrument which will show us the universe at low frequencies. Okay. In addition to the astrophysical part of the archive, I also passed through the part of the archive called Just Physics. And very often, by the way, astronomy-related papers are cross-listed to the astrophysical part, so you can just find them there. And in January, 2 interesting papers related to the history of science appeared in this part of the archive, and I want to tell you about them. One is dedicated to an old interview by Georges Lemaître. He's a famous cosmologist, one of the founders of the present-day cosmological model, together with Alexander Friedman and others. And of course, in his late years, he gave several interviews. And now you have an opportunity to watch a remastered video of his interview, which happened, as you see, nearly 60 years ago. And in the paper, they present also the script of the interview in 2 languages, so you can have a look at that. It's really quite interesting. The interview is quite short, but it's, I don't know, it's very impressive to watch these heroes of the past. So I strongly recommend you to spend a few minutes at least to look at the interview and to read the script, of course, because the interview is not in English, as you can imagine. Another paper about the history of science, and again about cosmology. That's the paper about Gliner. Gliner was a Soviet scientist with, of course, a very complicated biography, in some cases tragic, but finally I would say that with a happy second part of life. So he was under repressions during the Stalin period, and in late 60s he wrote several papers which are very important for the present day cosmological model, for the inflation inflation model, for the cosmological inflation. And the point of the authors is that these important papers are nearly forgotten. I would say that this is not the case. For example, Andrei Linde, one of the most famous present-day cosmologists, quite often referred to the papers by Gleaner, and there are many materials about him, so you can find it. But still, the paper is very interesting, really very interesting from many points of view. And in addition, it can give you a flavor about what was happening in science in the Soviet Union when significant scientific achievements were accompanied by different really tragic episodes in lives of scientists. So I strongly recommend to everybody to read this paper. It's not quite long and it's very interesting. It's in some respects it's kind of non-fiction. Of course, there are formulas. So for those who can really understand the importance of these papers by Gleaner, all necessary data is inside. But if you are not interested in this part, but more interested in general ideas and biography, you can just skip the part with formulas and enjoy the rest of the paper. It's quite interesting. So we are nearly coming to the end of this video, and what shall we talk about? Of course, we have to talk about the aliens. There were two interesting papers about the aliens. In the first, the authors presented a very huge, broad survey of stars, and they were looking for technosignatures. The survey was made in the framework of the famous Breakthrough project, and so they observed in radio nearly 1,000 stars, trying to detect some peculiar signals which can be interpreted as artificial signals. And actually, well, it's not fair maybe to say that they detected nothing, but most probably they detected nothing. They had 8 strange signals with which they plan to work more to observe these stars again, but I can bet that they will find some natural explanation. Natural also includes something happening in the Earth magnetosphere or technosignatures, but on the Earth. But still, this paper gives you a good impression what attempts people make to probe, to study in the observational way the problem of extraterrestrial intelligence now. So really the search is on and people are not forgetting it. And this is the observational side, and the second paper is really more interesting, but more. It's pure theory, purely theoretical paper. Here it is. I want to underline that Giyad Vali is a very famous physicist, really famous. So the idea here is quite interesting, and I'll leave you with this result that black holes might be a very interesting part of quantum computer for really advanced civilizations. We're not speaking about astrophysical black holes. We're speaking about microscopic black holes, which can be generated on colliders. And then they can be used to store information, because black holes are the best storage of information. That's really the best thing if you have to keep lots of information very compact and to read it very rapidly. And so in this paper, the authors developed such an idea that, so point number one, any advanced civilization must use powerful quantum computers. Then they must use black holes as parts of these computers. They might generate these black holes, and for that, they need powerful colliders, and that can be visible from the outside because there is a huge energy release accompanying production of black holes. And black holes, as they are macroscopic, they are evaporating. So you can also detect Hawking radiation. So the idea is that we have to look for such processes because they are kind of new technosignatures. So in the previous paper, people were looking for technosignatures suggested more than half a century ago by Shklovsky, Kardashov, Sagan, and others. But here, the authors suggest a new kind of technosignature, which is quite interesting. And even, well, Dvali would not be Dvali if he not suggest that even if this extraterrestrial intelligence are made of different particles, not protons, neutrons, and so on, but for particles which are invisible for us anyway, they might use black holes, and production of black holes and evaporation of black holes anyway produce radiation we can detect. So also funny, the interesting point of the paper is also you can look for invisible aliens if you are looking for evaporating black holes and their production. Okay, that's it. So I told you about some interesting papers published in the archive. You can look at these papers. In every slide and every screen you saw that there is a link, but what you are interested in is maybe just the number. For the last paper, let me switch again just to show it to you. It was 2301, which means 23 this year, 01 January. Dot, and then the number of the paper in the archive. So if you go to the website archive.org and put this number, you have access to this paper, and if you are interested in some of the subjects, you can have a look. Okay, that's it. Hopefully we'll come with a new video in a few weeks, or maybe in the end of February, beginning of March, to bring you some new interesting results, and you'll have an opportunity to look at them in details, going to the archive and reading an original paper, a review, or something like that. Okay, good luck.